Alright, so in this video what we're going to take a look at is the other part of the Lorentz force that we talked about in class. I want you to be able to not only find the value, the actual magnitude of the force, how strong of a force it is, but to be able to keep track of which direction that force is going to be directed in. So, we're going to take a look at a couple of different setups and use what we talked about in class, the right-hand rule, to solve them. Now make certain that you're using your right hand. For those of you out there who are naturally left-handed, it's especially important to keep track of that. But even beyond that, it's easy to make the mistake. And if you make the mistake, you'll end up with exactly the wrong answer. Okay, so the first one that we're going to take a look at is I'm going to have a positively charged particle. So you can imagine a proton. And it is going to be moving with a velocity like this. Here's my velocity vector. So it's kind of down and to the right. I have it moving through a magnetic field, which is up, straight up. And I want to know which direction the force is in. So, as a reminder, when it comes to the right-hand rule, we use that to describe the result of a cross product. And as a reminder, cross product looks like this, where we have vector C equals vector A cross vector B. So in our case, we want to find the force. We know that it was QV cross B. So we did the comparison in class where our first vector, that's going to be our velocity, that's going to be vector A. The second vector, our magnetic field, is the B vector. And finally, the force, it points the direction that our resultant, C, points. Now, for our right-hand rule, we apply it on any cross product. We take our right hand and we point it in the direction, we point our fingers in the direction of our first vector, vector A. In this case, for our equation, our first vector is going to be the velocity. So I'm going to point my fingers in the direction of the velocity. I'm going to point them down like that. The next thing I do is I curl my fingers, so I bring them in. I could go this way or this way. I could go all sorts of directions. But I want to curl them in the direction of my second vector, B, which in this case is my magnetic field. So I've got my fingers pointed in the direction of B. I curl them towards B, directly towards B, not going the long way around, but the closest that I can get to it. And wherever my thumb points, that's where the resultant is. So in this case, I point in the direction of B with my fingers, curl towards B, my thumb is pointed out of the board, and thus the force that this particle feels is out of the board. Now remember this notation, the circle with a dot, or just a dot by itself, is like an arrowhead coming at you. It's an arrow pointed towards you. The other one that we'll see, and in fact we're going to see it next, is the X with a circle around it, or just an X. Sometimes I may just use an X because that's easier to set up in Word documents. But you'll have an idea of what it is. So, the next one, we're going to have an electron, a negatively charged particle. So I'm going to make it a little bit more difficult for you. Its velocity is going to be directly to the right. And our magnetic field, this time, is going to go into the board. So we have a magnetic field directed into the board. Remember, this is the notation. It's like an arrow moving away from you. These are the tail feathers on there, or the fletchings. So you can see them as the arrows moving away from you, like an actual archery arrow. And I want to find out the force, the Lorentz force being exerted on this electron that's moving that way. Okay, so as we saw before, my first vector is my velocity, so I'm going to point the fingers of my right hand in that direction. Then I need to curl my fingers towards the second vector, which is going to be my magnetic field. Well, it's into the board, so I'm going to have a hard time curling my fingers that way. So I'm going to have to turn my hand like this. Now I can curl them in that direction. So my force that I predict will be straight up, except this rule applies for positive charges. When you're dealing with a negative charge, all you do is it goes the other way. So in this case, our force is down. So, as a reminder, right-hand rule, we point fingers in the direction of the first vector, our velocity, We curl towards our second vector, our magnetic field, which is into the board. And our thumb tells us which way a positive charge would go. It's the resulting force on a positive charge. And all we end up doing is we reverse that. Instead of up, we end up with down because it is a negative charge. Okay. One that I'm going to bring up real quick. You probably won't have anything that shows up in class that looks like it, but I'm going to have a positively charged particle. Our velocity is going to be straight to the right. And I'm going to have it move into a uniform electric field, or not electric, magnetic field, that is also to the right. We've got a problem with this. So I'm going to take my fingers and point them in the direction of the first vector, velocity. Then I'm going to curl them towards my magnetic field, my second vector, but I'm already pointed in that direction. I don't know what to do. Well, take a moment. Remember, the equation that we're actually solving, it's simplified down, at least for the values, to look like this. QVB times sine of the angle between them. What's my angle between these two? Well, they're both pointed the same way, so that angle happens to be 0. The sine of 0 is actually 0, which means it doesn't matter what the values are, my net force is actually 0. This is why it's important to say things like perpendicular, or keep track of those actual angles. If I have a charged particle moving into a uniform magnetic field, and they're both pointed the same way, or, alternatively, I could have the magnetic field point the opposite direction, so directly left. In that case, I'd have my hand like this, and I could curl this way, which would be out of the board, or it would be just as easy for me to curl the other way. Both are 180 degrees, and then it would be into the board. I can't really figure out between the two. Well, again, if I plug in 180 over here instead of 0, sine of 180 is still 0. I end up with no force. If the velocity is moving in the same direction as the magnetic field, it ends up having no force, no net force applied onto this charge. That's why whenever we look at them, we'll always see them where they're not quite going the same direction. Okay? So one of the final ones that we want to look at is finding the missing piece. So, for instance, I'm going to have a positive charge, and I'm going to tell you that that positive charge is experiencing a Lorentz force coming out of the board. So it's coming out of the board towards you. Okay? And that this is from it moving through a magnetic field, which is pointed directly to the right. Now, technically, there are a lot of different answers to this because the velocity could be in a bunch of different directions and still give us this result. But I'm going to tell you that our velocity needs to be at a right angle to these guys. So we're just going to do the reverse, basically. I know that my force, which way my thumb points, is going to be out of the board. This is a positive charge, so it's going to be out of the board. And I can just apply right-hand rule. I know that I need to curl my fingers in the direction of B, because that's my second vector. And so I need it at some right angle to these that would actually satisfy that. If I move my hand around, well, this would work, except my force is pointed the wrong way, so I've got to do this. So I need to I can move around until I find that the only reasonable answer is going to be that it's going to be straight down. That is, if it needs to be at a right angle to the others, which is more or less what we're going to deal with. We're mostly going to be dealing with right angles. Although one of the first ones that we had the velocity and the magnetic field kind of at different angles, but it should be all right. Okay? So, what you can do, the main thing I want to get across on this is you can find out the other information. Even with the force, you know which way to point your thumb, and you can start looking at how you would need to curl your hand in order to find these directions.